Today we're going to do an optimization problem. Those are word problems for Cal 1, but they aren't related to rates problems. They are finding the max and min and things like that, but in form of real world problems. So we're going today to answer the question, what is the minimum vertical distance, d, between these parabolas, y equals x squared plus 1 and y equals x minus x squared. And I've drawn them here. And the first thing that we really want to do is we want to figure out what exactly we're looking for. So looking at these parabolas, what is it that we're looking for? We're looking for the minimum distance, right? So we're looking for, here we have the distance between x and one of our parabolas, right? And then here we have a distance between x and our other parabola, okay? So what we're looking for is this distance, but not just the distance, but the distance of the point on the parabola here that is closest, like what point is closest to this point right here on the other parabola. That is what we want to know. So I hope that I explained that sort of understandably. Say that we have a point here, we want to know which point on here is the closest to it. Now, the way that we do problems like this is just with the formula. Like there's a formula that you have to know for this problem, and the formula is that the distance is the one parabola minus the other parabola, and it makes perfect sense. You've got the distance right here, and then you've got a distance right here. So obviously, the distance you're looking for right here is what you want to find. That's not the end. That's just our beginning, but that's what we have to do first. So I'm going to say find d. Okay, so let's just do that. Let's write it up here. d equals, let me make this y1 and this y2, right? So it equals y1 minus y2. y1 minus y2, which equals x squared plus 1 minus x squared. But we can simplify that, and it comes out to 2x squared minus x plus 1. Well, now what we have to do is we have to take the derivative of that. I'm not sure if that looks readable, so let me just do it again. Minus x plus 1. So now we have to take the derivative of d. And the reason we have to do that is kind of think about how we do it when it isn't a word problem, right? This is our original function, kind of. This right here is kind of the equivalent of our function. I mean, it is a function. This is our function. And when you take the derivative of it, that we're going to set it equal to 0. It's going to be how we find our critical points. So don't get confused. Don't get like, what exactly are we doing here? Because it's really just basics wrapped in a word problem bow. So the derivative of this equation right here, let me change colors. The derivative is going to be 4x minus 1. 4x minus 1. And the reason, of course, is that 2 times 2 is 4, and that makes the power 1, and then minus 1 comes from the x, and the 1 disappears. So now we're going to set that equal to 0 to find out what our x is. And we're going to add 1 to both sides, and we're going to divide by 4, and we're going to find that x equals 1 over 4. And that is our critical point, right? So we're trying to find the minimum here, which means we know there's going to be a minimum because that's how it's set up. So this is our critical point. And now we have to test it for whether it's a minimum or a maximum. Now, again, because of the way it's set up, it probably makes a lot of sense it's going to be a minimum. But in a lot of situations like this, you can do something wrong and end up with a maximum. And it's kind of good to understand that you aren't just checking it, like you can't just ignore what you get. Sometimes you get something weird and you've done something wrong, and you need to always like know what you're doing. So this is our critical point, and we're going to do a number line the way we always do. We're going to do a number line, test the intervals for increase and decrease. This is 1/4. So what we're going to do is we're going to take x equals 0, and we're going to take x equals 1. And we're going to test them. And we're going to test them on, note, we are not going to test them on the original function d. We're going to test them on d prime, right? Because we're testing the positive and negative slope. So we're going to take d prime of 0, d prime of 0, which is -1, which is smaller than 0. And therefore we know that from -infinity to 1/4, this is going to be a negative slope. And then we're going to take d prime of 1, which equals 3, which is greater than 0. And so we know, what color have I not used yet? I guess it's going to be green. That this is positive. From 1/4 to infinity is a positive slope. So that tells us that this critical point right here, 1/4, and this is very important, that tells us that we go from a negative slope to 0 to a positive slope, right? So that tells us we have a local minimum. Now, you need to check that, because sometimes I've done the wrong math and it's been the wrong way around and I've gotten a maximum and I've had to be like, wait, I was looking for a minimum. But here indeed we do have a minimum, so we know that at x equals 1/4, there is a minimum. Okay, so let me just write that down. At x equals 1/4, d has a minimum. But this is not the end, because we were asked what is the minimum vertical distance between the parabolas, right? So we actually have to plug 1/4 into our original function that we created, and that's not going to be hard. So let's just draw a vertical line here. Okay, so we're starting a new piece of work. We're going to have d equals 1/4 squared plus 1 in parentheses minus 1/4 minus 1/4 squared. And what that's going to come out to, it's going to come out to 17/16 minus 4/16 plus 1/16, which is, let me just skip all that and go to the second to last step, 14/16, which is 7/8. And that is the minimum distance between the parabolas. And I'm just going to go ahead and write that down. Minimum distance between y1 and y2. I hope that was helpful.